I'd like to introduce the components that make up the packing box and the piston. First, looking at the related valve body types, the reverse double-ported globe body is in Figure 1.9, and the flanged angle-style body is in Figure 1.10. Also, the three-way valve using a balanced valve plug is in Figure 1.11, and the body featuring a cage-style trim, balanced plug, and soft seat is shown in Figure 1.12. A complete packing box assembly includes packing, a packing follower, a packing nut, a lantern ring, a packing spring, and a packing flange, combined with some or all of the following: packing flange studs or bolts and nuts, a packing ring, a wiper ring, a felt wiper ring, Belleville springs, and an anti-extrusion ring. Individual packing parts can be seen in Figure 1.13. The piston is a movable pressure-responsive element that transmits force to the piston actuator stem, as shown in Figure 1.7.
These are the comprehensive packing material arrangements applied to globe-style valve bodies.
Let's look at the piston-type actuator. A piston-type actuator is a fluid-powered device in which the fluid acts upon a movable piston to provide motion to the actuator stem, as shown in Figure 1.7. These actuators are broadly divided into two types. One is the double-acting type, which can produce full power in both directions. The other is the spring-fail type, where the spring moves the valve in the required direction if the supply power is lost.
I'll now introduce the structure of the standard TFE V-ring and its resulting sealing characteristics. The TFE V-ring maximizes the sealing force between the valve stem and the packing through its unique V-shaped cross-sectional design, and provides high corrosion resistance for a wide range of fluids based on the chemical inertness of the TFE material. In particular, this structure reduces frictional resistance during the reciprocating motion of the stem to improve the control responsiveness of the positioner, while effectively blocking external leakage. I'd like to introduce the operation of piston-type actuators and the terminology for various valve members. Piston actuators are divided into two types. The double-acting method can produce full power in both directions, and the spring-fail method moves the valve in the required direction when supply power is lost. In terms of terminology, the plug is a general term for the closure member, and the port refers to the orifice that regulates the flow of the control valve. A retaining ring is a split ring used to secure a separable flange to the valve body. A reverse actuator is structured so that the stem retracts as diaphragm pressure increases, and a seal bushing is installed at the top of the yoke to prevent diaphragm pressure from leaking along the stem. A rubber boot is a protective device that prevents damaging foreign material from entering the seal bushing of the piston actuator, and the seal bushings come in a pair, top and bottom, to seal against leakage.
Let's discuss the sealing structure of the cylinder and terms related to the seat. The cylinder of the piston actuator is sealed to prevent leakage, and synthetic rubber O-rings in the bushings seal the cylinder, the actuator stem, and the stem extension. The seat refers to the contact area between the closure member and its mating surface that establishes the valve shutoff. Seat load is the net contact force acting between the closure member and the seat under stated static conditions. In practice, when selecting an actuator for a specific control valve, it is determined by adding a seat load allowance to the force required to overcome static, stem, and dynamic unbalance. The seat ring is part of the valve body assembly that provides the seating surface for the closure member and may also form part of the flow control orifice. I'll now introduce the separable flange and the spring adjuster. A separable flange is a flange that fits over the flow connection of the valve body and is generally held in place using a retaining ring. A spring adjuster is a fitting used to regulate the compression of the spring. It is typically mounted by threading it onto the actuator stem or into the yoke to adjust how much the spring is compressed. Both components are elements responsible for mechanical connection and adjustment in a sliding stem valve assembly.
I'd like to introduce some terms related to spring adjustment and trim. The spring adjuster is coupled to the yoke or stem to adjust spring compression, and the spring seat is a plate that holds the spring in position while providing a flat surface for the spring adjuster to contact. Static unbalance refers to the net force produced on the stem by fluid pressure acting on the closure member and stem when the fluid is at rest under stated pressure conditions. The stem connector is the device that connects the actuator stem to the valve stem. Trim refers to all the internal components of a valve that modulate the flow of the controlled fluid. In a globe valve body, this typically includes the closure member, seat ring, cage, stem, and stem pin. Soft-seated trim is a type of trim that uses readily deformable materials, such as elastomers or plastics, in either the closure component or seat ring to achieve tight shutoff with minimal actuator forces.
Let's look at the valve body and port configurations. The upper valve body is a half housing for internal valve parts with one flow connection. It usually includes a means for sealing against leakage along the stem and provides a means for mounting the actuator on the split valve body. The valve body is the main pressure boundary of the valve that provides the pipe connecting ends and the fluid flow passageway, and supports the seating surfaces and the valve closure member. Looking at the most common body constructions, a single-ported valve body consists of one port and one valve plug, while a double-ported valve body has two ports and one plug. A two-way valve body has two flow connections, one inlet and one outlet. A three-way valve body has three flow connections, used either as two inlets and one outlet for converging or mixing flows, or one inlet and two outlets for diverging or diverting flows.
The valve body is a core component that serves as the main pressure boundary of the valve, providing the pipe connecting ends and fluid flow passageway, while supporting the seating surfaces and closure member. In the field, it's often called just the body, but it is more accurate to call it the valve body assembly when referring to the valve body together with its bonnet assembly and internal trim parts. The valve body assembly consists of the valve body, bonnet assembly, bottom flange, if used, and trim elements. Here, the trim includes the closure member, which opens, closes, or partially obstructs one or more ports. The valve plug, also referred to as the plug, is another term for the closure member. The valve stem connects the actuator stem with the closure member in a linear motion valve, and the yoke is the structure that rigidly connects the actuator power unit to the valve. With these items, we conclude the sliding stem terminology and move on to terms specific to rotary shaft control valves. Next, we turn to rotary shaft valves.
From here, we will cover terms that apply specifically to rotary shaft control valves. First, the actuator lever is an arm attached to the rotary valve shaft that converts the linear motion of the actuator stem into rotary force to position the disc or ball of the rotary shaft valve. This lever is positively connected to the shaft, using methods like close tolerance splines to minimize play and lost motion. Next, a full ball is a flow-controlling member that uses a complete sphere with a flow passage through it, characterized by a flow passage that equals or matches the pipe diameter.
This drawing is an example of a rotary shaft valve structure, representing a conventional disc butterfly valve. In a conventional disc, a symmetrical disc rotates across the flow path to regulate flow, which is the most common disc type used in butterfly valves. Please note that this is an illustrative cut intended to show the shape of the parts without additional textual explanation.
This drawing shows the structure of an eccentric disc valve, and it corresponds to Figure 14, which collects typical rotary shaft control valve constructions. Due to the connection point between the shaft and the disc, the eccentric disc is designed so that the disc follows a slightly eccentric trajectory when opening. This allows the disc to move away from the seal quickly upon opening, reducing friction and wear.
These are typical configurations of control valves that use the rotary shaft method.
This shows the internal structure and operating principles of rotary shaft-driven control valves. A segmented ball is a flow-controlling member that uses a partial sphere with a flow passage through it. The most common type is the V-notch ball, where a polished or plated partial sphere surface rotates against the seal ring throughout the travel range. The V-shaped notch in the ball provides wide rangeability and produces an equal percentage flow characteristic. You can think of these balls and discs as performing a function similar to the plug in a globe-style control valve. In other words, as they rotate, they vary the size and shape of the flow stream by opening more or less of the seal area to the flowing fluid. Finally, a conventional disc is a symmetrical flow-controlling member used in the most common varieties of butterfly rotary valves.
Discs are divided into several types based on their shape. Conventional discs are typically limited to a maximum rotation of 60 degrees in throttling service due to high dynamic torques. On the other hand, dynamically designed discs are contoured to reduce dynamic torque at large increments of rotation, making them suitable for throttling service with up to 90 degrees of disc rotation. An eccentric disc, thanks to the positioning of the shaft and disc connections, follows a slightly eccentric path upon opening, allowing it to swing out of contact with the seal immediately to reduce friction and wear. Lastly, a flangeless valve is a common style for rotary shaft control valves. It is held between ANSI-class flanges by long through bolts and is also referred to as a wafer-style valve body.
I'd like to introduce the main design characteristics and components of rotary control valves. First, the eccentric plug style is advantageous for erosive applications because the plug cams into and out of the seat, which reduces friction and wear. Regarding flow direction, reverse flow can occur when fluid flows from the shaft side over the back of the plug. Depending on the valve design, it can either handle bidirectional flow, as is, or may require modification of the actuator linkage. Finally, the rod end bearing in the drive unit is a key component that converts the linear motion of the actuator into rotary force while minimizing lost motion. Therefore, when connecting a standard reciprocating actuator to a rotary valve, a linkage structure with two rod end bearings is typically used.
Let's look at the core components of a rotary shaft control valve. A rotary shaft control valve controls the valve capacity by rotating a flow closure member, such as a full ball, partial ball, disc, or plug, within the flow stream, and its structure is shown in Figure 1.14. To convert the linear thrust of the actuator into rotary force, rod end bearings are used. While a general reciprocating actuator requires two bearings when applied to a rotary shaft valve, an actuator specifically designed for rotary shaft service requires only one, which reduces lost motion. The component corresponding to the seat ring of a globe valve is the seal ring, and the position of the disc or ball relative to this seal ring determines the flow area and capacity at that particular increment of rotational travel. Some seal ring designs also permit bidirectional flow. Lastly, the part corresponding to the valve stem of a globe valve is the shaft, which rotates to position the disc or ball.
As we've seen, the rotation of the shaft determines the position of the disc or ball in the flow stream to control the valve capacity. A sliding seal is a lower cylinder seal in a pneumatic piston-style actuator designed for rotary valve service. It allows the actuator stem to move both vertically and laterally without leakage of lower cylinder pressure. Regarding flow direction, in rotary shaft control valves with a separate seal ring or flow ring, the direction in which fluid enters the valve body through the pipeline adjacent to the seal ring and exits from the opposite side is called standard flow or forward flow, which is distinguished from reverse flow. Finally, trunnion mounting is a method of supporting the disc or ball on the valve shaft or stub shaft using two bearings diametrically opposed.
Next, we turn to valve performance. Now, I'd like to introduce the terms used to describe the functions and characteristics of a control valve. Bench set is the process of calibrating the actuator spring range to account for the process forces that act during operation. Capacity refers to the flow rate through a valve under specified conditions, and clearance flow refers to the amount of flow that is lower than the minimum controllable flow when the closure member is not fully seated. Diaphragm pressure span is the difference between the high and low values of the diaphragm pressure range, and it can be expressed as either an inherent characteristic or an installed characteristic. A double-acting actuator is a type that supplies power in both directions. Dynamic unbalance refers to the net force produced on the valve plug by fluid pressure at any given open position. And effective area refers to the part of the total diaphragm area that actually contributes to producing the stem force.
The effective area of a diaphragm changes as the valve is stroked. It is typically largest at the start of the stroke and smallest at the end. Molded diaphragms are recommended because they have less change in effective area than flat sheet diaphragms. Equal percentage flow characteristic follows the definition provided in the process control terminology. Next are the safety-related operations. Fail closed is a condition where the closure member moves to the closed position when the actuating energy source fails, while fail open is the opposite, where it moves to the open position. Fail-safe refers to the characteristic of a valve and its actuator that ensures the closure member is fully closed, fully open, or remains in the last position, whichever is defined as necessary to protect the process, upon loss of the actuating energy supply.
Fail-safe action can also be implemented by using auxiliary controls connected to the actuator. Flow characteristic refers to the relationship between the flow through the valve and the rated travel, as it varies from 0 to 100%. This term should always be clearly distinguished as either inherent flow characteristic or installed flow characteristic. The flow coefficient, CV, is a constant related to the geometry of the valve at a given travel and is used to determine flow capacity. To be precise, the CV value is the number of US gallons per minute of 60 degrees Fahrenheit water that flows through a valve with a pressure drop of 1 psi, or 1 pound per square inch. A high recovery valve refers to a design that dissipates very little flow stream energy due to its streamlined internal contours and minimal flow turbulence.
A high recovery valve is one where the pressure downstream of the vena contracta recovers to a high percentage of the inlet pressure thanks to the streamlined internal contours. Straight-through flow valves, such as rotary shaft ball valves, are typical examples of high recovery valves. Inherent diaphragm pressure range refers to the high and low values of pressure applied to the diaphragm to produce the rated valve plug travel when the valve body is at atmospheric pressure. This range is often called the bench set range because it is the range over which the valve strokes when placed on a workbench. Finally, inherent flow characteristic refers to the relationship between the flow rate and the travel of the closure member as it moves from the closed position to the rated travel, under the condition that the pressure drop across the valve remains constant.
Here, I will introduce the diaphragm pressure range and the flow characteristics under installed conditions. Installed diaphragm pressure range refers to the upper and lower limits of the diaphragm pressure that produce the rated travel while specified conditions are acting within the valve body. Due to the process forces acting on the closure member, the inherent diaphragm pressure range and the installed diaphragm pressure range can differ for the same valve. Installed flow characteristic refers to the relationship between the flow rate and the closure member travel as it moves from the closed position to the rated travel, while being influenced by varying process conditions that affect the differential pressure across the valve. Leakage is covered under seat leakage. Linear flow characteristic is covered under linear characteristic in process control terminology, and a low recovery valve refers to a valve design that dissipates a considerable amount of flow stream energy due to the turbulence created by the flow path contours.
Next, I'd like to introduce pressure recovery characteristics, modified parabolic flow characteristics, and push-down to close construction. In low recovery valves, the pressure downstream of the vena contracta recovers to a lower percentage relative to the inlet value. While designs vary, conventional globe-style valves generally exhibit this low-pressure recovery characteristic. Modified parabolic flow characteristic is an inherent flow characteristic that provides an equal percentage characteristic at low closure member travel and an approximately linear characteristic for the upper portions of closure member travel. For normally closed valves, please refer to fail closed, and for normally open valves, refer to fail open. Push-down to close construction is a globe-style valve configuration where the closure member is located between the actuator and the seat ring, such that extension of the actuator stem moves the closure member toward the seat ring, eventually closing the valve.
Now, let's look at push-down to open construction and rangeability. Push-down to close can also be applied to rotary shaft valves. In this case, linear extension of the actuator stem moves the ball or disc toward the closed position, so it is also called direct acting. Conversely, push-down to open construction is a globe-style configuration where the seat ring is located between the actuator and the closure member. When the actuator stem extends, the closure member moves away from the seat ring to open the valve. When applied to rotary shafts, stem extension moves the ball or disc toward the open position, and this is also called reverse acting. For quick opening flow characteristic, please refer to the process control terminology. Rangeability is defined as the ratio of the largest CV to the smallest CV within a range where the deviation from the specified flow characteristic does not exceed set limits.
Next, I will introduce the quantitative expression of rangeability and terms related to the flow coefficient. If a control valve still performs well even when the flow increases to 100 times the minimum controllable flow, that valve has a rangeability of 100 to 1. Rangeability can also be expressed as the ratio of the maximum controllable flow rate to the minimum controllable flow rate. Rated flow coefficient, or CV at rated travel, refers to the flow coefficient of the valve when it is at rated travel. Rated travel is the distance the closure member moves from the closed position to the rated full open position, and this rated full open position is the maximum opening recommended by the manufacturer. Relative flow coefficient is the ratio of the CV at a specific travel to the CV at rated travel.
Here, I'll introduce seat leakage, spring rate, stem unbalance, and the vena contracta. Seat leakage is the amount of fluid passing through a valve when it is in the fully closed position under specified differential pressure and temperature conditions. ANSI leakage classifications are summarized in Chapter 5. Spring rate is the change in force per unit change in spring length. In diaphragm control valves, it is typically expressed in pounds force per inch of compression. Stem unbalance refers to the net force produced on the valve stem in any position by the fluid pressure acting upon it. The vena contracta is the section of a flow stream where fluid velocity is at its maximum and fluid static pressure and cross-sectional area are at their minimum. In a control valve, it normally occurs just downstream of the actual physical restriction.
Finally, I'd like to introduce other process control terms and standard abbreviations not covered previously. Among the terms listed here, those marked with an asterisk are quoted from the ISA 51.1 Process Instrumentation Terminology Standard, while the others are terms widely used in the control valve industry. ANSI stands for the American National Standards Institute, API for the American Petroleum Institute, ASME for the American Society of Mechanical Engineers, and ASTM for the American Society for Testing and Materials. An automatic control system refers to a control system that operates without human intervention. A Bode diagram is a plot of log amplitude ratio and phase angle values on a log frequency axis for a transfer function, and it is the most common way to graphically represent frequency response data.
We will now explain various technical terms used in control systems through graphical representations.
I'd like to introduce some calibration-related terms used to quantify the performance of a control valve. First, a Bode plot is a graph that displays the log amplitude ratio and phase angle of a transfer function on a log frequency axis. It is the most common way to graphically present frequency response data. Next, a calibration curve plots the steady-state output of a device as a function of its steady-state input, and is usually expressed as % output span versus % input span. A calibration cycle refers to the process of applying known values of the measured variable and recording the corresponding output readings in both ascending and descending directions across the entire instrument range. By varying the input in both directions, we can obtain a calibration curve that allows us to measure hysteresis. I'll now introduce some other process control terms frequently encountered with control valves and instrumentation. Clearance flow refers to the flow that is below the minimum controllable flow when the closure member is not seated. A controller is a device that automatically regulates a controlled variable without human intervention. Regarding thermodynamic quantities, we have enthalpy and entropy. Enthalpy is the sum of a body's internal energy and the product of its volume and pressure, expressed as H equals U plus PV, and is also called heat content. Entropy is a theoretical measure of energy in a thermodynamic system that cannot be transformed into mechanical work. A feedback signal is a return signal resulting from the measurement of the directly controlled variable. In a control valve with a positioner, this usually takes the form of mechanically feeding back the closure member stem position to the positioner. Finally, FCI is the abbreviation for the Fluid Controls Institute.
Now let's look at terms regarding the dynamic behavior and stability of valves. Frequency response characteristic represents the amplitude and phase relationship between steady-state sinusoidal inputs and the resulting fundamental sinusoidal outputs as a function of frequency. By varying the input test frequency and observing the output amplitude and phase shift, we can describe the dynamic behavior of the control device. Hardness is the degree to which a metal resists plastic deformation, primarily through indentation. For plastics or rubber, it refers to the resistance to an indenta point penetrating the surface. Hunting is an undesirable oscillation of significant magnitude that persists long after external stimuli disappear. It is also called cycling or a limit cycle, and serves as evidence that the system is operating at or near the stability limit. In control valve applications, hunting appears as an oscillation in the loading pressure to the actuator caused by instability in the control system or the valve positioner.
Along with hysteresis, I'll introduce some standard organizations and pressure terms. Hysteresis is a phenomenon where the effect of a change in forces acting on a body is delayed, similar to viscosity or internal friction. ISA was the abbreviation for the Instrument Society of America and is now recognized as the International Society for Measurement and Control. Regarding pressure terms, we distinguish between instrument pressure and loading pressure. Instrument pressure is the output pressure from an automatic controller used to operate a control valve, while loading pressure is the pressure used to position a pneumatic actuator, which actually acts on the diaphragm or piston. If a positioner is not used, the loading pressure may be the same as the instrument pressure. Also, NACE originally stood for the National Association of Corrosion Engineers, but as the organization became international, it changed its name to NACE International and is no longer an abbreviation. OSHA is the abbreviation for the Occupational Safety and Health Act in the US.
Finally, I'll introduce terms for operating media, limits, range, and repeatability. The operating medium is the fluid, generally air or gas, used to supply the power to operate a positioner or automatic controller. Operative limits refer to the range of operating conditions a device can withstand without permanent impairment of its operating characteristics. Range is the region between the limits within which a quantity is measured, received, or transmitted, expressed by lower and upper range values. For example, 3 to 15 psi, minus 40 to plus 212 degrees Fahrenheit, or minus 40 to plus 100 degrees Celsius. Repeatability is a measure of how closely a number of consecutive output measurements agree for the same input value under the same operating conditions when approaching from the same direction.
I'd like to introduce the measurement method for repeatability, along with the concepts of sensitivity, signal, and signal amplitude sequencing. Repeatability is measured during full-range traverses. It is typically measured as non-repeatability and expressed as a percentage of span, and it does not include hysteresis. Sensitivity refers to the ratio of the change in output magnitude to the change in input that causes it after the steady state has been reached. A signal is a physical variable where one or more parameters carry information about another variable that the signal represents. Signal amplitude sequencing, or split ranging, is an action in which two or more signals are generated or two or more final controlling elements are actuated by an input signal, with each responding consecutively, with or without overlap, to the magnitude of that input signal.
I'll introduce 4 terms frequently used with control valves. First, span is the algebraic difference between the upper and lower range values. For example, if the range is 0 to 150 degrees Fahrenheit, the span is 150 degrees Fahrenheit, and if the range is 3 to 15 sig, the span is 12 sig. Next, stiction is the force required to cause one body in contact with another to begin to move. Supply pressure is the pressure at the supply port of a device. Typical values are 20 sig for a 3 to 15 sig range and 35 sig for a 6 to 30 sig range. Finally, zero error is the error of a device operating under specified conditions of use when the input is at the lower range value, and it is usually expressed as a percentage of ideal span.